This is, I think, sixth class on the course, the electromagnetic field theory and transmission lines. So we are almost in the midway of the module one. So in case of electrostatics, um, some of the few things you have to keep in mind that the the point charge and the continuously distributed charges and what are the differences. All these things you can understand through not just by remembering the formula or the equations which are derived, but all the time you have to get practiced with some numerical workouts, some situations like if a line is given at this particular plane and what is the electric field at this particular point, like that actually there will be so many numerical problems required. And in fact, that is going to come in the exam as well. So you have to practice all the time. And another important fact you're supposed to remember is the speed what you're going to do in the exam. That is very, very important because that is going to give you even if something goes wrong, and then you can save the time and you can finish up that same problem itself. So in on the way of the classes, I will give some tips here and there whenever we go, so that you can also keep that in mind. You can also apply for all the courses as well. Yeah, in case of electrostatics, we started with the Coulomb's law. The Coulomb's law described the force acting on a particular charge due to another source charge, and that is purely depends on three things. One is uh, the the charges actually which are participating in that source and test charge, and the distance and the line joining between them. And the third one is the material which is available at there. So that is not, as of now, it is not yet come here. So in future, we will see that there will be one of extra term is going to add here. So we will see those things, some material physics part will come that at that time. We move to uh, the the force acting on a particular uh, test charge due to multiple charges and how to describe that. So the key thing you have to remember is sometimes these points will be given, or sometimes the R vector itself might be given. And this is actually completely vectorial or mostly pure mathematical workout. So you should be a little careful about where it is starting and where it is ending and how to get the vector values correctly, all these things. So you just need a huge amount of practice, not just by one or two, you can't understand that. So keep on do that, even if a numerical problem is available, let's say some numerical problem like this, you just again do that, again do that, again do that, so that you will be practiced with how to do a numerical problem easily. And then we move to defining the field distribution around a particular charge. And if another charge is coming into the picture, how this field distribution will change itself in such a way that it makes the linkage, and this linkage going to be uh, useful in order to describe the behavior of force, the electric force. There comes if the charges are freely moving, then it will be attracted and repel. And the very important question what we supposed to ask is, if a atom is made up of positive and negative ions, then what makes these two charges not attract to each other? There are some special behaviors or coming into that is what we call as quantum theory. There comes many more parameters like quantum numbers, like including spin theory. All these things will come into the picture. So it's a very important argument, and there comes the importance. And the electric field hereafter will come throughout the course in various forms. So this is one of the very essential concepts uh, in this theory. This example we already have seen. Today we are going to see multiple examples which are solved mostly with this definition, that is Coulomb's law. And the next one, what we have studied in the last class was the electric field due to continuous charge distribution. So if your charge is distributed over a surface or over a line, with a uniform, sometimes non-uniform case also. So how to describe that? There are two general questions will be asked, like what is the total electric field at a particular point due to this line charge or surface charge or volume charge. And the next one is what is the total charge density available. In the next class, we are going to see that what about the how this total charge density and the electric field, how they are actually highly relevant. In fact, you will also see that this electric field and the charge are more or less same. And this also create a, I think this could be starting off that this particle wave theory, dualities all the way. The very first problem what we have seen is we have to find the electric field due to a line charge. So in this case, the line is taken at an arbitrary point. Okay, the point can be anywhere you can take. Maybe you can take from in the x-axis or y-axis, anywhere else. So to avoid making at the origin point, so it is taken at the particular point A to B. So, and in that case, how this electric field at a particular point, and this point also chosen as an arbitrary point like X, Y, Z axis, so that this point can be moved to any place. Here, throughout the direction, any direction you can move. So in that case, we can easily find what about the electric field around the a line charge. So what we have started with the basic definitions, and we have converted that into easier workout by converting that to cylindrical coordinates, and then we have calculated the electric field in terms of that. We did some mathematical workout, and finally we got the electric field due to finite charge, finite line charge. Okay, this finite line charge here, the XYZ axis is completely gone, and you have only this vectors. Finally, this cylindrical vector coordinates alone is available, and rho is rho L is the charge density, and rho is the distance of the particular point P from the line in the so this is actually the distance with respect to the if we draw a perpendicular line for the line vector. So if we draw a line vector for this, okay, so if we draw a line vector, and this line vector will keep on going. So this is the axis, Z axis, the perpendicular line. So in the line with respect to the line vector, if we draw a perpendicular line such that it will meet the point P, then that distance is rho. So this distance and this R are completely different. In fact, one has to work out on that. So in order to avoid that contradiction, because this distance R will keep on change with respect to this alpha change or this question, everything. So that is why it is done with it. It is a one. This particular derivation will be very, very useful because this is going to come in multiple applications. When you work on transmission line theory, when you work on antennas, when you work on some of the, in future, we will study some resonance or resonators. So those places also, this particular equation will come and will help us. And some special case also we have seen that if we take a infinite line charge. So if we take an infinite line charge, what is actually happening is this, we take an infinite line charge, wherever the point P can be located, and it obviously will come under this any particular point such that the rho is meeting a perpendicular line. So this point, anybody can easily take as a center point, so that at any location, and this location, let's say here you are taking a DL, and exactly at the same distance you are taking another DL, then the corresponding electric field components will be cancelled. Sorry. So this they generally be cancelled out. So therefore, this AZ component, this is actually the Z direction. Therefore, along this only a z vector will be there. So this, there are two components. One is this direction and another this direction. One is this az vector. So due to this az vector, due to this maybe minus az vector. So they cancel each other. So by the way, only this vector survives. And when we substitute that values of alpha and alpha 1 and alpha 2, we obviously will get this equation. That's the interesting part in this one. And here it is purely depends on the distance from the one line. We also did very similar workout for infinite charge density. And I'm not going to explain again. So here also we can see the very similar behavior, kind of canceling out on both the sides. And finally, what we should understand is the electric field, induced electric field due to the surface charge with the charge density of this. And so that is here the 4 pi is gone, only 2 left, and epsilon naught is available. And even this height, at what height this electric field, sorry, the particular point of observation is also gone. So this indicate that the electric field, if this is the sheet, infinite sheet, which is very, very large. So we will assume this is L and this particular point P is here and this height. So even we can take some very large value, maybe 2h. So even at this particular point, if this length is too large than h, and several times, maybe 10 times, 20 times like that, then obviously this is quite feasible, and the h become meaningless here. So electric field will be always uniform throughout that and for an infinite distance. So that is what we can understand out of that. However, the question about the size of the sheet, all these things are highly questionable. Then if we do for volume charge, so we are going to do the very similar workout. And in case of sheet charge, the advantage is the sheet is infinite. And since the sheet is infinite, obviously the cylindrical, you can't put any cylinder shape or you can't put any spherical shape. If you put a spherical shape, then it will cut into two halves and it is very difficult to coordinate it. So for this, the rectangular coordinate system is correct. And the similar way, if you take the line charge, and for line charge, the cylindrical coordinate system is the optimum one. Okay. Similarly, if you take the volume charge, and the volume supposed to be surrounded, so that is what the indirectly which we are going to do. So the volume can be surrounded by a three-dimensional sphere, and therefore the cylindrical coordinate system is much more suitable for volume charge integrations or electric field due to volume charge. So this simply follow the Coulomb's law itself. So if you refer the Coulomb's law and you will and the corresponding electric field expression, you will get that instead of here you will get r square, and here you will get the source charge, that is small q will come. So that's the difference. Now we are actually going to see some of the simple numerical problems, and you're supposed to consider that these questions are already discussed or going to be discussed like that. So you may not expect the same similar behavior in the exam. So you're supposed to go beyond that, and I will give some tips how to do that. So here there is a question given like a finite sheet. So we have seen for infinite sheet, but here comes with a finite sheet. So the sheet is defined like this. So it is defined from 0 to 1 and 0 to 1 and 0. Sorry, in the x direction 0 to 1. So we have a x-axis, and similarly we have a y-axis and z-axis in the perpendicular. So here 0 to 1 and 0 to 1. So this makes a square. So here it is having a charge density, surface charge density, which is actually defined. This also highly defined with respect to x and y axis. And so, and then along the z axis, we have the point P. and which is located at a height of 5, okay, unit 5. So here it is not mentioned anything, but it is mentioned like meter square something. So we can call it, it is in the meter or centimeter. There is no unit is given, okay, in particular for this coordinate system. So in this case, how to calculate the electric? First, we have to calculate the total sheet charge density, then electric field due to that. And so this 1 cross 1, if you consider with respect to the height, it is not sufficiently large. So that is one thing you have to quickly remember, so that there is a field component might exist all around the direction of the XYZ direction. So first we are calculating the total charge density. So total charge density we always calculate with respect to the surface charge density into this the small area, which is nothing but the unit area over the space. So that is given as dx dy. You should always remember this ds expression will vary for uh, coordinate system to coordinate system. So I always advise you just you make a small chart. It is best to do now because that chart you can use it throughout the semester. So for DL, in case of we can say dx, dy, dz, like that actually we can do. But in case of the same DL, in case of a line vector, in case of a cylindrical coordinate system, we will mention like d into d phi like that. So here the DL corresponds to d phi with respect to the radius like that. So this kind of table is supposed to make it. Then you can easily substitute them, then you will easily get the answer. And if some vectorial concepts are coming into the picture, then you can put vectors also. So this is supposed to be integrated over the given space, and charge density is given and the ds is given. And the nanocoulomb is given to say that uh, the entire integration going to be done over the this particular units. And by the way, uh, so the integration is very simple. We are going to do for first x, then y like that, or even you can do independently because both are completely. So here, whenever you get it in 1/2 or 3/2 like that, so the best advice is make this x dx as dx square. So you can easily, so dx square will give us 2x 2x dx will come. So by the way, this x and this dx can be described when this 1/2 has come. So like this, actually, when you work out in more mathematical way, rather than complicated integrations, you will get answers quickly. So this practice is what we are expecting in the exams. So then we are actually integrating on both the sides, and after substituting, we are getting the total charge density. Sorry, total charge out of the square sheet. Now we are actually calculating the electric field. So when you calculate the electric field, uh, so the electric field uh, is calculated. You can simply see the at any particular point. Okay, so we are going to take a sheet. The sheet is like this, and with respect to this particular point, P is here. So this is x direction, this is y direction. So the sheet at any particular point, okay, we can assume this particular point. Let's say this value is yes, not yes. You can give something else. You can give some a. So this particular point a, in order to describe this any of the place, so a can be defined as x comma y comma 0. So for y equal to 0 plane, x can be available at anywhere else, and the x is also limited within 1 to 1 only. It will exist, so that we can control over the integration. But in order to define the sheet how it is distributed, we can define like this. So this is actually so this is the point P, and this is the line joining vector. Sorry, this is the line joining vector, and this vector we are going to call it as a r vector. Okay, so this r vector has can be calculated as because this particular point and this particular point. So this is, we know that we can call it as x 0, 0, 5. And this is actually x, y, 0. So the answer for the R vector is nothing but, so this is the starting point, this is the end point. So we generally get minus x ax vector minus y ay vector plus y ac vector. So this is the R vector. And this is, so this vector is going to be in this direction when it is here. When this point is here, it may go like this. So it may go like that. It may go so multiple. And at overall, we have to calculate the total electric field at the particular point due to this sheet charge. So that is what we are going to do. So the electric field. So the charge density is here, and this ds is here, and this ER vector is going to define this vector. Okay. So here it is given with capital R. It's better to do with small r. And then 4 pi epsilon naught, we can easily see that. And it's better to calculate this 1 by k equal to 1 by 4 pi epsilon naught. This most probably you can easily calculate yourself and you can do it. Then we are going to substitute this r square. So the magnitude of this you can easily substitute. Okay. So which is going to be x square plus y square plus 25. Okay. So that is going root of. So that is going to be the magnitude of the R. So we have written this. So here there is a typical expression for R minus R vector. So here this is describing this R vector and R dash vector like that. So we have ignored that part. Simply we have written as R. So in this case, it is given as rho s ds divided by 4 pi epsilon naught and the R vector divided by magnitude of R whole cube. Like that it is given. Okay. So with respect to this particular problem. In the book, actually, they sometimes over exaggerate the expression itself. So it is up to you. Okay. So this is why you need some little practice to understand yourself whether you are doing correctly or not. So now we are going to substitute. So we have substituted this nano Coulomb. Then this is the rho s, and so this is what the R vector, and this is ds and 4 pi, and so this is nothing but yeah, this is the epsilon naught, and this is going to be the magnitude of the R. So all these things were expressed. So you can see here this and this is quite same. So we are going to cancel out. And when you cancel out this, you will get 9. So this 9 will go up. So you got this 9. And this 10 power 9 and this 10 power 9 got cancelled. And just remaining thing, you have to integrate it. Okay. So we are going to integrate over the x. So first actually this xy. When you multiply with this x, you will get minus x square y. So minus x square y is integrated. Then like that, actually, this 3 different terms were integrated and the unit vector kept as if. And finally, you got this integration done, and this is the value. So all instead of ax, ay, they have given in the point form. So this also vector only. So to make sure that you always express this electric field in terms of vector. And this value is calculated, but we are actually multiplying this. So minus 9 by 6, all the value substituted, and volt per meter has come. So this volt is constant common one, and the meter comes since it is a given with a meter square. So this kind of small Okay. So by this, we got the electric field. Okay. And the force is very easy to calculate. The force finally we have to multiply with the test charge. At particular point P, what charge is available? So this is the charge. You can mention this is a capital Q. This is a test charge that we are multiplying. Since we are multiplying with millicoulomb, so you will get it in millinewton like that. So it is very easy to do that. So what are the key things you're supposed to remember in this workout is the way you do the mathematical uh, integration all the way. So otherwise the problem is very, very simple and substitution of all the cases. And so this actually need little practice. The format and all the way it's supposed to be very neat. And so after finishing this, many people used to do this in different way. So finally, how you got this answer? If this answer is correct or not, I never worry about that. Okay, even if you get wrong answer, but if these steps are correct, I'm sure that you will get the maximum mark. That is not the problem. The problem is the procedure what you follow. And since the procedure comes into the picture, then obviously this all will take time. This drawing, writing this integration and x square dx, all these things will take little extra time. So that time you have to manage. Okay, so that is a very important thing. This not only applicable to, since I am saying that you should not simply follow to my course itself, you have to follow for all the courses. Then only you can expect good marks. Even when you defend for marks also, it will be very useful. The same similar work actually you can practice. So here the square plate is described in this way, so that so the total length, so the total dimension is about 4 cross 4. And carry a charge density and the total charge we have to calculate and the electric field intensity at this particular point. So the answer is also given. You can work out by yourself with a very similar procedure, whatever the procedure. So in order to confirm your way, what my best recommendation is you work out and take a photo and send through WhatsApp. Okay. So when you do that, you just always do like how you are going to do in the exam so that you can get the concurrence easily. Actually this problem purely I created. Yesterday night only I thought, okay, how this problem will work out. And so, so like this, actually, we can create a number of problems. Okay, so in the exam, almost infinite possible questions are possible within the scope of complexity only. Gives the final thing like marks, size of the question, all that. So a line charge is actually of length L. So arbitrary length is not mentioned, and is placed such that its center uh, in the origin. Okay, so the exactly it is in the origin, so that in the right side it is going to be L by 2. In the left hand side it is going to be L by 2 and oriented in the y direction. So this can be x direction, y, z direction. So even if it is not mentioned, you can take any direction. Okay, so here it is particularly mentioned as y direction. So we are taking as a y direction. Find the electric field at a particular point P, 0, 0, hertz. And we know that the center is already located at the origin point, and exactly just above that, the particular point P is available at 0, 0, hertz. So that this corresponding height is known, and find the electric field as a function of L and H. So that is what we are intent to do. So how to do that? So this is actually completely not a we can say it is pure numerical workout. It is more what we call analytical workout. So we have to do some derivation out of that. So whenever you do some derivation like this, first of all, you're supposed to free of mind with respect to numbers. You should not define any size for this. And this, whenever this length is increasing, it's supposed to increase on both the sides. All these proper, what do you call, the physical definition supposed to be understood, then you have to work out. So this kind of new questions, if it is comes to exam, and your approach will be evaluated, not the answer. I remember, I repeat that uh, the answer is purely how you describe the problem and how you work out the problem that comes. So can anyone suggest some idea that how to do this workout? Because similar finite length we already done over here. Is it? Can someone help how we can do this workout?
So we take a small element on the on the line charge sheet. Uh, uh,
Okay.
yes, due to symmetry, there would be an opposite small element due to which the electric field would cancel along the y direction. So the resultant field would be in z direction only.
Mm.
So then we have to, sir, introduce the line charge density Q equal to rho LDL.
Yeah. Yeah, that's
Uh,
really good workout. And so here you're supposed to describe the cylindrical behavior so that the row vector will come. Okay. So all these things. And that's really good work actually. So this problem look like big, but it can be easily solved considering the fact of the earlier workout. So that is one procedure. And but before saying so that this selecting DL and taking the opposite, first you have to describe the if we take this particular DL and if we draw a line joining, let's say this is equal to R, then this will be having two vectors. One is a row vector, another one is, let's say, this direction. So this is actually a y vector or yeah, a y vector like that. So there will be two vectorial components will be available. Then, therefore, if this is all correct, then exactly opposite side, there will be another. So you will be getting uh, two times and the cancel one will be taking place like that. So that is what you have to properly say. And of course, uh, when you work out, for you will not say anything. You know that how the answer is supposed to be done. And as a professor, when you say that, I will also understand. But in the paper, when you write it in the so-called exam paper, you're supposed to think that you are going to talk to a person who is not at all knowing this. So at least within the scope of mathematics and some way of with the knowledge of electromagnetic field theory, you have to start the derivation. So you need a framework. Okay. Otherwise, if there is a formula is known, you can substitute the formula and solve the problem. And that too highly depends on the marks. If this question asks for 15 marks or more than 10 marks, you're supposed to do the entire derivation for a arbitrary point. And if the arbitrary point is coming in this 0, 0, hertz with respect to the line, then how to do that? All these work out together. And if the mark is 5 marks, then you can substitute well-known formula and you can reduce that. So like that, you have to understand the importance of that. Okay. Here, same similar question answered in another way. So we know this particular problem for which the line is placed at arbitrary location, not and its center is not available in the origin or somewhere else it is. And this particular point is also arbitrary. Okay. So for an arbitrary located transition, sorry, yeah, line charge and arbitrary point, we already have the expression for that. Okay. Since it is an open book test, you can quite away you can take it. So this we have to uh, connect with our problem. So our problem is that we have the xy axis, xyz axis, and we have kept the line. And so this line vector is, or the projection is going to be ay vector. And the next thing is, it is the point P is located at a height from the line. And so this, so, and this problem, we have point A and B. So here also we are describing at point A and B. So when you do that, you draw the same line, this vertical one, if you put here in this side, so AB will come here only. When you change to AB this side, you will interchange the alpha 1, alpha 2. So then some minor problems will come. That is up to your understanding. So this A, B, both are substituted. Then we are having this point P. So this point P, and it is located exactly in the just above the origin point at a height h. So here, obviously, we will easily understand this rho is equal to h. So this rho, first we have to describe the rho. So rho is equal to h is defined. Then we are going to map the alpha 1 and alpha 2. So for that, we can take the alpha 1 and alpha 2. Otherwise, here I have taken new angles because there will be a plus or minus difference will come. That is why. So since A is this particular point, I have taken this psi 1 here and psi 2 here. Then alpha 1, and definitely it is going to be psi 1. So we know this particular point, if it is available here like this, then this is the line that is nothing but TP. Okay, so with respect to that, this is alpha 1, and with respect to that, this is alpha 2. So negatively, negative 1 will come. So that is we have to keep in mind. So this alpha 1 is equal to psi 1, and I'm taking this value as psi. The psi value we can easily triangulate since height and length is known. This is L by 2 and this is h. So anybody can easily say that it is tan inverse of L by 2 h. Then alpha 2 is going to be psi 2, and but it is the opposite, negative side. So negative sign. And we know that this length is exactly divided by half. So psi 1 and psi 2 both supposed to be same. So psi 1 equal to psi 2, which is this here it is psi, here it is going to be minus psi. That's all. Since this constant is going to keep on come, so I'm going to take this value as k, which is, do you know anybody what is the constant name? 1 by 4 pi epsilon naught. Okay, so that is called Coulomb's constant. Well, so we got this three important variables of this equation. This rho is known, alpha 1 and alpha 2 both are known, and this two unit vectors we will keep remind. So but in the future we're supposed to change that. Okay, because for example az vector we can't take because it's supposed to be ay vector and with respect to this direction. So we are substituting all these expressions in this. So rho we are substituting as h, and this is alpha 2, and this is alpha 1, alpha 2, alpha 1. So we can easily see that. So sine psi, which will become minus sine psi. So it will become 2 sine psi, minus minus will give 2 sine. And this is cos minus psi. So we know that the value will be cos psi. And this also already cos psi. Both will cancel each other. It will give 0. So you can see that the one what he said, they will cancel each other. Here it is mathematically coming naturally. So this ay component, naturally it will be lost. And this rho vector, which is a vector which is perpendicular to this line. So it is commonly referred with the an vector. So this an vector, to calculate that, you're supposed to find the line vector which is perpendicular to this. And when you substitute that, then you will get it. So that is nothing but the EL vector. This vector sign is very, very important. Then we are actually substituting what is this psi. So the psi is tan inverse of L by 2. So this is more than sufficient. If you get the answer up to here, that is more than sufficient. But yeah, if you are good in so-called mathematics, then you can also further work out. But you should not bear the means you're supposed to be come up with some good approximation. Otherwise, the problem may go wrong. So This is actually one of the intense standard. I think you people solve this particular problem, sine tan inverse of x like that. So from that day onwards, I always remember this because it is, I always argue with my professor that my teacher. Okay, so here it is 1 square plus x square. So why can't you take this simply nothing but 1 by x, 1 plus x itself like that. So he always say that this bounded with some numbers. So you can't do that like that. So I still remember that discussion. So sine inverse of tan inverse of x is this, and this is subject to that this is having perfect match for the values within 1 plus 2 minus 1. Within that limit, it will perfectly fit. But beyond that also, sometimes it will fit, but that is out of the scope. So to reduce this complex trigonometry workout into simple xy, so we have substituted here. And then this 2h square will become 2h simply. And when you cancel out, you will get this. This is the expression for the electric field in terms of L and H. And provided it is not accurate one, this is actually approximate one. So that is why I'm saying that you can stop here, no problem, but you can also say that this also optimally correct. But how to say both are correct? So you're supposed to draw using MATLAB or some other workout. When you do that, you will see that how far these two expressions are meeting each other. And when you substitute L equal to infinite, you will see that this L equal to infinite case means it is definitely very, very larger than 1. In that case, it will become L square. So the L square will become L after root of. So L will be cancelled. So this can be approximated to 1. That is very well known unity. So by the way, you will get this expression where k is nothing but 1 by 4 pi epsilon. So 2 will be cancelled, this equation. So this quite same. I think you can still remember that this the expression we have taken for L for infinite length case. So this also quite a good answer or approximate answer. Uh, and if you plot more, actually you will see so many interesting behaviors. So here you can see that this two expressions, sine tan inverse of x and x by root of 1 plus x square, both are plotted here. So both are overlapped each other. Okay, so here also you can see the blue line and red line both are overlapped. It is almost perfectly matching. After some time here, after some small minor change you can see, but it is almost 99%. We can say that they are matching. So this is a not even approximation. We can say it is quite same. And sometimes you can't see the blue line, so that is why I have put this extra line to see that how the pattern looks like. So the interesting fact is that just after the till L, that is the length of the line and the height. Okay, so you can call it as this is L by 2 and this H. So L by 2 H. So when uh, L by 2 equal to H. Okay, so that is the meaning. So when this two are equal, then you got the value of 1 for the X, and there comes the up to there it is linearly increasing. The electric field will increase linearly. After that, the electric field will start to slow down, which means it will start to saturate and it will become almost constant. And this constant will go up to the length infinite. And this is supposed to be the magnitude of that, which is about 1 time. Okay. So that what makes uh, this correlation. Okay. So and when you increase this h, so when you increase this h about 2 times, 3 times, so it will go like that. This will go like this, and this value will keep on go down because it is indirectly proportional and linearly indirectly proportional. So that is what we have to see that. So the magnitude of the electric field decided by the H, not by the length. So that is quite interesting. Okay. But that is solely applicable when the length is sufficiently large. Okay, so then they cancel each other and the H again come into the picture. So this kind of quite interesting. So so this is what makes you more electrical engineer rather than a numerical workout. So you can also cross check this derivation again if there is a mistake. This purely I did yesterday night. I didn't sleep, so just I have worked out it. And so similar kind of numerical or analytical questions can be asked. So if uh, the next question you can see here. So this is another simple question that if there is a square loop and uniformly charged. Okay, so here the charge density is given, and then so it is a loop. It is not like square plate. It is a loop. So it is made up of 4 lines. So you can call it a segment 1, 2, 3, 4 like that. And what about the electric field at this particular point? Okay. So all these 4 segments, they are going to the vertical components of them, the arrow vector, they are going to add up here, and some other components will cancel each other. So you can easily work out. But this problem you have to triangulate with the proper mathematical procedure. So if you try that, and if you show me, then I will help you whether it is correct or not. Even I haven't done it, but this kind of questions you can expect. Maybe if it is a triangle one, if it is a circular one, so how it going to come. And another problem, what we have seen, there is actually, if there is an infinite line, if there is an infinite uh, one, then we know the corresponding electric field. Okay, so the corresponding for length, for surface, all these things. So we already know about that. So this is going to be rho L divided by 2 pi epsilon naught rho. And this is going to be 2 rho s. Okay, I'm sorry. Rho s by 2 epsilon naught. Okay, so here there are 3 uh, two sheet charges, infinite sheet charge, and 1 infinite line, and their locations are given. And you have to calculate the electric field due to this 3 hybrid distributions like line distribution and infinite sheet distributions like that. And this sheet is located at uh, where it is actually it is x equal to 2, and this is actually located at y equal to -3. So this is actually some far away, and this particular point is uh, 1 comma 1 comma, that is within the line, means within this. So if you see from top, so you will see like this. So we are going to draw that. So first we will draw the y-axis, sorry, z-axis. So how to draw the z-axis? Anybody has the idea? If we see from the vertical side. Okay, so this is the origin point. If you draw a circle, then that is going to be the perpendicular vector. This, so it is like this. So in the back side, if you see arrow mark, so if it is if you're drawing from the bottom side, then you can draw the same z vector as like this, like that, center point. Then we have this x-axis, y-axis. So -3 is here. So there is an infinite sheet, and another infinite sheet is crossing this side, and there is a line that is going this way. So this particular point P is here, approximately here. So how to calculate this one? So you have to be clear that you have to find out this distance and find out this distance and find out this distance. And that is what you are going to substitute here. And here there is no need to substitute because they are all already infinite. So you can easily get the problem. Okay. Finally, you have to worry about only the vectorial direction. So I think to even this and this perpendicular vector also we supposed to see into that, because this is not it is not available in any particular axis. So this problem you work out, you will get little 10 like 2. That's all. So I think this class went little interesting, might be. So you just tell your opinion about that, maybe in the WhatsApp or something like you feel these problems are difficult, or you feel these problems are very easy, so that we in the next class we can improvise that. So you can ask any questions, and the class is already over. You can leave if you have any other work now. Thank you.
Thank you, sir.